Thank you, Michael. I'm delighted to present the new technologies of the KROHNE Group. Ladies and gentlemen, I would like to extend a warm welcome to you all. Over the next 20 minutes, I will show you what the Internet of Things could mean in process automation, how microsystem technology as an enabler for smart sensors serves to ensure more efficient plant control, and how new imaging methods provide more insight into your processes. The fourth industrial revolution, also called Industry 4.0, the integration of all physical and virtual elements of process automation, is already a reality. Industry 4.0 focuses on the creation of intelligent products and processes. People, machines and resources are able to communicate with each other in an obvious way, as can be seen today in social networks. However, such complex systems can only be realized with decentralized modular intelligence. This is the basis in process automation for the profitable production of customized products, even in small quantities. I will give you an example from the food and beverage industry. Today on the Internet, I can already configure my own custom-made beer. I can freely choose the type of beer, the intensity of the hops, the alcohol content, the fizziness, and its color. I can even print my own personalized label. Let's look at how the filling process happens today and how it could look like in the future. For the filling process, you need a flow meter and behind it a valve. These are both individually connected to the PCS. The measuring device provides the current flow rate to the PCS, which sends the open and close signals to the valve. The combination of controller, flow meter and valve therefore forms a control loop. We can now integrate this control loop into the measuring device. The PCS still sends the information about how much liquid should be filled, but the measuring device opens and closes the valve independently. Together they form an intelligent filling module. Do you remember the instrumentation and control module that Stefan mentioned earlier? Well, what you're seeing here is nothing more than a special type of the general instrumentation and control module. In order to ensure that I'm really filling my favorite beer, I can now add an inline analysis system which measures the beer's turbidity and alcohol content, for example. The ERP then sends a message to the customer, for example, via WhatsApp, notifying them when the beer will be delivered, along with a link to the analysis report. This customized product manufacturing process places high demands on the flexibility, the quality, and also the costs for such a module. Therefore, the next logical step is the integration of all functionalities into a single device. The inline filling head automatically takes a fingerprint of each filling. So, for every bottle I have an analysis that I can clearly refer to. But what does this have to do with chemistry, you might ask? Quite simply, analysis and traceability are essential parts of the filling process. If I manufacture a herbicide, for example, I have to retain samples. Within the scope of legal regulations, these samples can be partially or even completely be replaced by the use of an intelligent filling head. The problem is that the laboratory equipment used today is not suitable for integration in field devices, especially not the complex analyzers for the substance composition. Microsystem technology is a key technology that had been studied since my university time, so for decades now. Back then we incorporated optical emission spectroscopy into a monocrystalline sapphire chip. Using this well-established microsystem technology, you can manufacture chemical analyzers significantly cheaper, which are also much smaller in size, Only then can they be universally used as field devices in the chemical sector. Let's stay with the example of herbicide, where multiple chlorobenzene compounds are required for its manufacture. The synthesis of chlorobenzene is widely used and shall serve us as a guide here. Essentially, it can be divided into three parts. Firstly, the benzene is dried with hydrogen chloride, and afterwards the hydrogen chloride gas is washed out. Then, the actual reaction of chlorine and benzene to mono, di and trichlorobenzenes takes place. Finally, the reaction products are separated from each other using multiple distillation. Let's look at chlorobenzene synthesis in more detail. But don't worry, even non-chemists will be able to follow the presentation. The raw materials are benzene and chlorine gas. In the main reactor, they react to form hydrogen chloride and chlorobenzene with a range of byproducts and isomers. For this reaction to take place, I need dry benzene. A sophisticated drying process is therefore located upstream of the main reactor. I extract the water from the benzene by introducing hydrogen chloride, which is formed as a byproduct of chlorobenzene synthesis. The hydrogen chloride gas is then turned into hydrochloric acid through absorption in water. This hydrochloric acid can be resold as an important basic chemical. I am able to verify that this byproduct is low in organic contaminants by using a flame ionization detector. However, even today, a relatively complex construction is still required, for example in an analyzer cabinet. With the help of microsystem technology, it is possible to integrate this in a much smaller space. Through this miniaturization, the creation of a field device is already within easy reach. Let's now take a look at how the miniaturized flame ionization detector is constructed. This is how it could look like as a field device with a microsystem technology chip built in. For the combustion process, I introduce hydrogen and oxygen, represented here in blue and green. The hydrogen flame burns between two electrodes. Since no ions are emitted during the combustion of pure hydrogen, the flame initially has no conductivity. Despite the electrical voltage applied, no current flows. Now, if we introduce the sample, shown in red, into the hydrogen of the flame, there is now a very small current flowing. The current is a direct measurement of the organic carbon concentration in the sample. By integrating this into a field device, we have developed an inline measuring method that can be used at many points in the plant. Other potential applications for the micro-FID include, for example, leak monitoring of the heat exchangers. This will detect traces of chlorobenzene in the ppm range, for example, through hairline cracks, and helps to detect any small damage at an early stage. It is not the only analysis technology that can be miniaturized. I will show you another research project by the example of the chlorobenzene synthesis. The main product, chlorobenzene, is formed in the main reactor and in the secondary reactor downstream. Non-converted benzene and the hydrogen chloride formed are returned from the reactors and separated in the separators. We obviously don't want chlorobenzenes to be returned here. How well the chlorobenzenes are separated, in other words, the efficiency of the separator, can be monitored using a mass spectrometer. Similar to FID, a relatively complex construction is still required even today. Here, microsystem technology also helps to achieve integration into a much smaller space. And again, we are close to creating a much smaller field device. In this example, we have simply copied the method used for the FID. We can also apply this principle to other complex analyzers. Now let's look at how a miniaturized mass spectrometer works. We generate free electrons, which are shown here in red. These electrons collide with the molecules of the sample. The molecules are ionized and broken down into individual fragments. The molecular fragments are shown here in color. Each color represents a molecular fragment with a certain mass. The ionized fragments are accelerated in an electric field. The speed achieved depends on their mass. The heavy ions are slower than the light ions. Now we need a speed filter to distinguish the masses from each other. For this, I use an electric field which is applied vertically to the ion stream. This does not remain in one place, but travels along the ion stream. All ions that fly into the electric field are extracted. Depending on which ion mass I want to allow to pass, I only have to vary the speed at which the electric field moves through the structure. The downstream detector registers a current flow, which is invoked by the incoming ions. The current is a direct measurement of the concentration of the ions. In our animation, we first see the signal peak of the heavy ions. Equally, we can capture the concentration of the lighter ions and therefore record a complete mass spectrum of the material we are analyzing. Using intelligent databases, the substances can then be derived from the mass spectrum, which can be used for better process control. Other possible applications of the miniaturized mass spectrometer include, for example, purity monitoring of reactants, as well as inline quality control of the various products. Through multi-stage distillation, the different chlorobenzenes are separated. The para-dichlorobenzene, which is solid at room temperature, can be separated from the mother liquor by crystallization. This crystallization process cannot be monitored using conventional field instrumentation. However, I will show you a completely new method which makes this possible. Tomographic methods allow us to gain insight into the interior of a reactor. Using capacitive impedance tomography, for example, I can measure the permittivity in crystallization containers in a spatially resolved way. Let's look at how this permittivity distribution can be determined. The mechanical construction is fairly simple. I need a ring of electrodes around the container, which are dielectrically separated from the substances in the vessel. In this way, I avoid generating a current flow in my product. I can also use my field device to determine the permittivity distribution in non-conductive products. For this, I need low-frequency signals, which are generated and measured directly at the electrodes. Let's take a look at what happens inside. For simplicity, we have illustrated only 3 solids in the mother liquor. If I now apply a low-frequency signal to an electrode, I can determine the electrical capacity with respect to all other electrodes. This leads to the permittivity distribution shown on the right. The spatial resolution is still quite low, which is why the solids shown here still appear blurred. By activating more electrodes, the spatial resolution increases and the image becomes sharper. If I increase the sampling frequency, I can even trace the changes over time in the vessel, such as the movement caused by the agitator. Of course, a realistic image of the vessel looks a lot more complex. With capacitive impedance tomography, we have developed a technology that makes it possible to visually trace the crystallization process almost in real time. The demonstrator shown here is just one of our many achievements from the close collaborations we have with researchers at universities and institutes. In the exhibition, you will be able to see the galvanically coupled impedance tomography for yourselves. Tomographic methods can also be used for detecting air or gas entrainments. Air or gas entrainments occur much more frequently in a process than you'd think. They were one of the most common causes behind our service technicians being called out to check a supposedly defective flow meter. I will demonstrate how we solved this problem. After the crystallization process, I obtained the para-dichlorobenzene via a centrifuge. At the downstream flow measuring point, the mother liquor can temporarily contain entrained air as a result of the centrifugation. Without this entrained air, I have the desired regular oscillation of the tubes in the Coriolis mass flow meter. Air entrained in the liquid dampens the regular oscillations of the measuring tubes, and as the air content increases, it finally comes to a complete stop. To overcome this, we have developed powerful control algorithms. These algorithms allow us to uphold the oscillations and measure up to 100% air entrainment. So even throughout a complete transition from a pure liquid phase to a gas phase and back, that is, from 0 to 100% gas content, the device will continue to perform without ceasing to measure. You will be able to see this process live in action on the model in the exhibition. At this point, I would just like to mention that if you are interested in the details of this technology or any other technologies presented here, you are cordially invited to attend our workshop presentations. Entrained gas management was a short excursion to the present day. It is already available in field devices. I would now like to introduce to you another future technology which we are currently bringing to market. Let's look at the entire chlorobenzene synthesis once again. One of the reactants is benzene, which is mainly derived from crude oil. The measurement of crude oil directly at the borehole is a big challenge, because the crude oil does not flow out from the borehole in a pure state. Typically, it is a mixture of oil, water, sediment and gas. What interests me, however, is the quantities of oil and gas extracted from the well. Until now, I could only measure this after separation in a separator, which can take up to a week. With the help of our new technology, this takes just a few minutes, and also before the separator. Using magnetic resonance technology, we have developed a multiphase flow meter that operates in real time. As mentioned previously, the main components of the flow from the well are water, sediment, oil and gas. For simplicity, we will restrict ourselves to oil and water. Let's look at how we can distinguish these two substances in the flow. Both contain bound hydrogen. The nucleus of the hydrogen consists of only one proton, which has a positive electric charge. Due to the intrinsic rotation of this proton, a magnetic moment is created around it, the so-called nuclear spin. Without the influence of an external magnetic field, this magnetic moment can point in all spatial directions. If a magnetic field is applied, this magnetic moment aligns itself parallel or antiparallel to the magnetic field. However, there is always an overlay of these two states. Now, we will look at a variety of protons as a whole. Imagine we would summarize all magnetic moments at their origin. Without an external magnetic field, this would result in the displayed image of an arrow resembling a hedgehog. When a magnetic field is applied, the arrows start to align with increasing field strength, leading to a small magnetization. This is represented by the arrow, which grows out of the hedgehog in the direction of the magnetic field. We illustrate this further by the coloring from magenta to blue. More blue means strong magnetization. Please remember that for a moment. But let's look first at the structure of our multiphase flow meter. For a very basic explanation, imagine a non-metallic measuring tube with a permanent magnetic field applied. The magnetization of the multiphase mixture can be read out using high-frequency signals. When the oil and water molecules flow from the left through the magnetic field, the bound hydrogen is magnetized and colored in blue. This magnetization with oil-bound hydrogen takes place faster than with water-bound hydrogen. Therefore, at the end of the magnetic field, the oil is more strongly magnetized than the water. The hydrogen atoms behave differently depending on how they are bound. This is the principal effect we use to distinguish the substances. In doing so, we have built a substance-specific flow meter. This inline multiphase device is already used in the oil and gas industry, with a huge potential to increase well efficiency, since you can adjust the extraction rate much better. In the future, this measuring method will also be made suitable for use in other industries. In the exhibition, we brought an example which you can see and touch, and in the workshop we will explain how we determine the gas content. To conclude, I would like to highlight a problem that is directly related to such high-performance measuring methods. Let's look at the process one last time. Methods such as magnetic resonance or impedance tomography generate a lot of complex data, which current process control technology is unable to exploit to its full potential. If the morning shift transfers 1 second of an impedance tomography sequence via heart, it will take as long as 15 hours, so it will only just be available for those on the night shift. Even with field bus, you could go off and have lunch while you're waiting. I can only make use of this data through more intelligent networking. Let's see what classical wiring looks like. Each field device is connected to the control system via a slow, although safe, point-to-point connection. Communication between the field devices is not provided. By setting up another communication network which, to make things simple, can be set up wirelessly, I can transmit large amounts of data much faster and also enable communication between the field devices. An additional high-speed network, wireless or wired, opens up many new possibilities, for example with completely new value-added services. Just like smartphones and the underlying high-performance communication network have opened up a whole new world of services, I can also imagine a variety of new business models. This, in my view, would not be possible without the guidance of NAMUR. Otherwise there will be chaos in the App Store. The sensor technology of the future will generate huge amounts of data in a plant with several hundred measuring points. This data will not only be the primary measurements from the sensors, but a whole host of additional information. To be able to utilize this amount of information, we need context-sensitive viewpoints or filters that split this data into its various roles. In this way, the plant operator will continue to receive primary measurements via the slow and safe field bus network. The process optimizer will look at the same plant, but will receive tomographic data via an additional network, which will give him much more insight into the process. In this way, he will have many more possibilities available to optimize and feed better settings to the plant operator. Via the additional network, the asset manager will also receive information on the device status or on the condition of the system with regard to corrosion, leaks or fouling. It will even be possible to make conclusions for predictive maintenance and to give early warnings to the plant operator. Of course, you can imagine a lot more than these 3 points of view. The system is also freely extendable, and the technical possibilities will inspire all of us to create new concepts with added value. The potential of automation technology in the chemical industry is far from being exhausted. I am confident that we will be able to set things in motion. The sensor network remains the foundation to obtain the necessary information and is the basis for big data. From big data, we make intelligent data. We combine the physics of measurement with plant models. Knowledge-based controlling of plants will become a reality. Has this technological overview helped you to guess which molecule and which spectrum we showed you at the beginning? If the answer still eludes you, perhaps you can have a think about it during the break over a cup of coffee. But before you get to enjoy that much-needed caffeine, we would like to thank you very much for your attention.